Learning Outcome 2, Functions and Algebra, 12.2.7. A. Investigate and use instantaneous rate of change of a variable when interpreting models of situations. B. Use the following rules of differentiation. D. Generate sketch graphs of cubic functions using differentiation to determine the stationary points, maxima, minima, and points of inflection, and the factor theorem and other techniques to determine the intercepts with the x-axis. E. Solve practical problems involving optimization and rates of change. Welcome back to our calculus series. MacGyver will be helping us again today. Hi, MacGyver.
Hi. So what are we going to be doing today?
Well, in this lesson, we will be using all of the knowledge and skills that we have developed over the previous 8 lessons to solve our problem. If you remember, I made a comment at the beginning of our series on calculus about how calculus was invented to solve problems.
Yeah, I remember. We did a problem just like that when you did the box problem.
That's right. And today we're going to look at another problem and see how calculus can be used to solve it. This should help us to tie up everything that we have learned. By the end of this lesson, you should be able to solve a practical problem involving optimization by means of rates of change. To start out with, we need a problem. So I'm going to tell you a story that will introduce us to a problem. The problem that we are going to deal with involves predicting the population of a bug. The professor that you can see there has been monitoring the bug population in this garden over many months and has kept a record of the population in terms of how many hundreds of the bugs there are per square meter. He has plotted his findings on this graph here, and as you can see, the population seems to have increased in the early months and then decreased for a while before increasing again. And here comes the professor. Let's see if I can ask him a few questions. Professor, do you mind if I ask you a few questions about your work?
Sure. I love my bugs, and I love talking about my bugs. Bugs make my world go round.
Right. But why are you so interested in knowing the population of the bugs?
These are very friendly bugs, and they help the plants to grow. If we know what happens to their population, we can know when to give the plants additional supplements and so on. What we have also noticed is that the population varies in cycles. See, if we start here, then the population first increases. It reaches some maximum and then decreases before finally increasing again.
Very interesting.
What your viewers will be interested in is that I have developed a model, an equation that pretty much predicts the population. Here, let me superimpose it on the data. As you can see, most of the data points that I have collected lie on or near this line.
They do, but what happens over here? The points have stopped and the graph carries on. Will the bug population simply increase and increase and increase from here on?
No, it won't. For the population to increase, there needs to be enough food to feed my bugs. They are very hungry bugs, you know. After a while, the bug population gets so big that there's not enough food and the bug population cannot increase anymore. So, although the graph suggests that the population could increase, in reality, it cannot. To avoid any confusion, I do this. I use this red graph to show the time for which the equation of that graph describes the behavior of the population.
Do you think that I could be given the equation of that graph for use in my lesson with the viewers?
Now you're just ruining a friendship. It has taken me years to find this formula, and now you just want to take it and use it. I don't think my bugs would like it either.
Wow. Just as we were starting to get along, the professor is quite possessive of his formula.
Yeah, right. He got a little tense there.
I guess that he has spent so long developing the formula. Now he wants to use it to help farmers make predictions and then charge them for his advice.
So what predictions do you think you might expect to make?
To give you a sense of the kind of information that a farmer might be interested in, I have formulated a question. Let me show you.
Don't tell me you pinched that formula from the professor.
Let's not talk about that and just get on with the problem.
Oh, okay, but don't call me when the professor lets some unfriendly bugs loose in your bed. The problem asks us to determine after how many months the population will reach a maximum, and then how many months later it will reach a minimum. Isn't that like finding the turning points?
I guess that it is. Do you want to give it a go?
Okay. We have shown that the turning points occur when the gradient of the tangent to the curve is 0.
Good. And how do we determine that?
Well, that is what the whole series has been about, isn't it? Finding the gradient of the tangent to the curve. And to do so, we have developed what we call the derivative.
I guess that you're saying that we developed a technique for determining the derivative, and that we can use the derivative to find where the tangent has a gradient of 0.
And that is where the graph has a maximum or minimum value, a turning point.
Let me remind you, we said that the derivative is the gradient of the tangent to the function at any point. Notice that the derivative is also a function, denoted f dashed of x. And so, the first step in solving the problem is for MacGyver to determine the derivative or gradient function.
So, I'm going to start by writing this as 4 separate terms so I can differentiate the function. So, it becomes x cubed divided by 8 minus 18x squared divided by 8 plus 60x divided by 8 plus 592 divided by 8. Now I'm ready to differentiate. Let me start by writing f dashed of x equals. Now I will differentiate the function term by term. Let me start with x cubed divided by 8. This 3 becomes to the front, and I get 3 times x to the power of 3 minus 1, which gives me 3 times x to the power of 3 minus 1, all divided by 8. The next term is 18x squared divided by 8. Again, this 2 comes to the front, and I get 2 times 18x to the power of 2 minus 1, which gives me 2 times 18x to the power of 2 minus 1, all divided by 8. The next term is 60x. Now the exponent, which is 1, even though it is not written here, comes to the front, and I get 1 times 60x to the power of 1 minus 1, which gives me 1 times 60x to the power of 1 minus 1, all divided by 8. And finally, I have this constant, and the derivative of any constant is 0. So I can simply write plus 0. Let me tidy all of that up.
Well, it looks like Magava's getting pretty confident with the steps in that differentiation process. You also need to be able to do so with confidence, and you will develop confidence through practicing. What next?
My reason for finding the derivative was to use it to determine the x values of the turning points of the graph, because they correspond to the maximum and minimum value of the function.
Although that statement is not quite correct, let's carry on. I'll show you what I mean by not quite correct later on.
Okay, well, what I do know for sure is that the derivative is 0 at the turning points, although you prefer to call them stationary points.
Great. So
I suppose that I should set the derivative equal to 0 and solve the equation. At the turning or stationary points, the derivative has a value of 0. That is, f dashed of x should equal 0. In other words, 3x squared divided by 8 minus 9x divided by 2 plus 15 divided by 2 should equal 0. If I multiply this equation by 8, I will lose the denominators and get 3 is clearly a common factor. So let me divide the equation by that. And I get 'an equation that can be factorized as x minus 2 times x minus 10, which implies that either x minus 2 equals 0 or x minus 10 equals 0. And it follows that either x equals 2 or x equals 10.
nice to see that you're doing all of that with such confidence. Well done. Now what?
Well, I've answered the question because I know the population is at its greatest after 2 months and at its least after 10 months.
Really? How do you know that with such certainty?
Just think back to the professor's graph. It first went up. In other words, the population increased to a maximum, and then it went down. The population decreased to a minimum. So the 2 or 2 months corresponds to the maximum value, and the 10 or 10 months corresponds to the minimum value.
Although Magava isn't wrong, he only knows that the maximum value occurs after 2 months, and the minimum occurs after 10 months because he has seen the graph, and for no other reason. In most cases, when solving a problem like this, we don't have the graph to start out with, and hence need to develop strategies for determining which of the x values of the turning points corresponds to the maximum and which to the minimum turning point. Magava, what I would like to do is to have a look at 2 different techniques which we could use to determine which of those x values corresponds to the local maximum and which to the local minimum.
Great, but I have an idea.
What is that?
You know how you said that I only knew the x value which corresponded to the local minimum and corresponded to the local maximum because I had seen the graph?
Quite right.
Well, say I had not seen the graph, then drawing the graph would have helped me conclude what I concluded by seeing the graph.
Correct.
So, what I'm thinking is, why don't I just carry on as if I'm going to draw the graph? That is, why don't I just determine the y values of the 2 turning points, and then the point which the larger y value will correspond to the local maximum, and the point with the smaller y value will correspond to the local minimum.
Fantastic. And that is precisely one of the two methods that I wanted to discuss. Why don't you get on with doing those calculations?
Well, there you have it. After 2 months, the population will be 75. And after 10 months, the population will be 49. So the population will be greater after 2 months than it is after 10 months. And since these correspond to the turning points on the graph, it follows that the population reaches a maximum of 75 after 2 months and a minimum of 49 after 10 months.
Of course, the model gives the population in hundreds of bugs per square meter. So it would be better to say that after 2 months, the population reaches a value of 7,500 bugs per square meter, or 7,500 bugs per square meter, and 4,900 bugs per square meter after 10 months.
Of course. Okay, so if finding the actual function values of the turning points is one way of being able to compare the points in terms of the maximum and minimum, what is the other way you had in mind?
Well, this method uses at the rate of change of the function what we discussed in our last lesson. Let me try to show you what I mean by drawing this number line here. Now, below the line, I'm going to write down the x values, and above the line, I'm going to record the value of the derivative. Now, you calculated that the derivative is equal to 0 when x is equal to 2 and 10. This line corresponds to an x value of 2 and a derivative value of 0.
And I suppose that this mark then corresponds to an x value of 10 and a derivative value of 0 in the same way.
Correct.
So far, we have marked the x values that correspond to the turning or stationary points on the line, and noted that the derivative has a value of 0 for these x values. What next?
Well, what I want to do next is to determine the value of the derivative in these intervals. That is, for values of x less than 2, for values of x between 2 and 10, and for values of x greater than 10.
Didn't we do that sort of stuff in our grade 10 and 11 work? What were we working on when we did that?
I'm impressed that you remember. We were working with inequalities there.
That's right. But when we did that, we didn't write the actual value of the expression. We only wrote whether the expression was negative or positive.
And we're going to do the same here. Do you remember how we did that? We simply took one x value in the range, substituted it into the expression, and determined whether the expression value would be positive or negative. We were not really interested in the actual value.
Oh, I remember. Let me start. I'll take this first interval and choose a value for x of 0. Then the expression. In this case, the derivative will... Where is that equation? Ah, here it is. When x is equal to 0, the derivatives will have a value of, this first term will be 0, the second term will be 0, and the last term is positive. So the derivative will have a positive value, which I will record here, like this.
Let's leave Magava to do that for the other regions. In our last lesson, we looked at how the derivative value and the slope of the graph are related. In particular, we showed you how when the graph slopes up as we move along the graph from left to right, it has a positive gradient, and the derivative has a positive value. And similarly, how when the graph slopes down as we move along the graph from left to right, it has a negative gradient, and the derivative has a negative value. Let's now incorporate that onto the number line.
Okay, I'm done.
Well done. What you have determined is that in this region, when x is less than 2, the derivative will have a positive value. And in our last lesson, we showed how a positive derivative value corresponds to the graph sloping upward as we move along the graph from left to right.
I am with you.
I'm going to show that on this number line by drawing a line that slopes up like this. In other words, the graph slopes up.
In that case, in the region between 2 and 10, the graph will slope down because the derivative has a negative value. And I can show that by drawing a line that slopes down, like this. In other words, the graph slopes down.
And similarly, the graph will again slope up in this last region because the derivative has a positive value in this region.
So, how does that make us see that the turning points at x equals 2 is a maximum and at x equals 10 is a minimum?
Well, just think about it. As we go along the number line from left to right, so this line that we have just drawn in suggests that the graph will increase, go up, until the point where x equals 2, and after that it will go down. In other words, the function reaches a maximum value and then starts decreasing.
Pretty cool. And similarly, as we keep going along the number line from left to right, so this line that we have drawn suggests that the graph will continue to go down until x equals 10, and then it'll go up again. In other words, the function value gets as small as it is going to get, and then increases again. A minimum turning point.
And another way of determining which of the turning points will be a maximum and which will be a minimum, a method that relies on our understanding of the derivative value.
Which leaves me with one unanswered question. My reason for finding the derivative was to use it to determine the x values of the turning points of the graph, because they correspond to the maximum and minimum value of the function.
We'll stop there for a second, because that's an important idea that you just identified, and I want to discuss it for a bit. Have a look at the graph that the professor drew. He said that although the graph was the graph of this model, his equation, it was only useful for times between 0 and 14.5 months. He emphasized this by highlighting the relevant portion of the graph with this red line. Now, can you see that although the population reached a maximum value of 75 after 2 months, here, when x is greater than 14, in other words, after 14 months, the function value is greater than 75. That is, the population will be greater than 7,500 bugs per square meter.
Ah, I see what you mean. And that is why we introduced the term local maximum and local minimum earlier. In terms of our problem, we could say that during the first 14 or so months, the population reached a maximum after 2 months and then started decreasing. But with time, and assuming that the population continues to behave according to the professor's model, the population can reach values greater than the value reached after 2 months.
And the key thing you said there is that all of this is only true if the population continues to behave as the model predicts. In this case, the professor did suggest that the model was not useful beyond a certain point.
If we call this turning point the local maximum, what would you call this maximum value here?
We would call that the absolute maximum in the interval that is of interest to us. For today's task, I want you to solve a very similar problem to the one that Magava and I have been working on. And that brings us to the end of our series on calculus. I hope that you have learned a great deal and that you have come to see that calculus can be a powerful tool for solving problems. Goodbye.